Okay, imagine this. What if a problem that takes a massive supercomputer literally a million years to solve could be answered in just minutes? Well, that's exactly what happened when D-Wave's quantum prototype went head-to-head with the Frontier supercomputer to tackle a highly complex magnetic materials simulation. The classical supercomputer would have needed an absolute eternity, plus more electricity than the entire world uses in a year just to crack it. The quantum system? It did the whole thing in minutes. So, the quantum era isn't just some far-off science fiction anymore, it's an impending, very real reality. Welcome to this explainer. Today, we're taking the quantum leap. We are stepping way beyond the theoretical physics chalkboard to look at exactly how quantum computing is actively redefining tomorrow. We're going to see how it's fundamentally transforming the industries we rely on every single day. I'm super excited to guide you through this, so let's jump right in.
Here is the roadmap for our Quantum Leap Tour. We're kicking things off with Beyond Classical Computing Limits. Then, we'll cover Combating Climate Change Faster, Accelerating Aerospace Product Design, Optimizing Complex Financial Markets, Sensing Earth from Space, and finally, wrap up with The Coming Societal Transformation.
Section 1. Beyond Classical Computing Limits. Hitting the wall of traditional processing. The quantum train is leaving the station right now, and the speed is honestly staggering. In 2023, IBM demonstrated quantum utility, which basically means quantum computers started performing reliable computations that go way beyond brute force classical methods. Fast forward to 2025, and D-Wave publishes a paper actually proving quantum supremacy on a real-world problem. All of this momentum sets up a massive commercial annealing boom predicted for 2026, leading straight into IBM's projection for fully fault-tolerant, error-corrected quantum computers by 2029. The urgency for industries to adapt is incredibly real.
Now, to really wrap our heads around how this works, think of basic metallurgy. If you want to harden iron, you heat it up to increase the molecular speed, right? And then you slowly cool it down to stabilize those stronger bonds. Well, quantum annealing does this exact same thing, but with energy instead of temperature. It's constantly seeking out the global minimum, or the lowest possible energy state. It's a method perfectly designed for massive combinatorial puzzles, like the classic traveling salesman problem. It can almost instantly find the most efficient route among billions of possibilities by leveraging quantum tunneling to pass straight through energy barriers, rather than climbing over them.
Section 2. Combating Climate Change Faster, from sequential petabytes to parallel quantum kernels. The leap we're seeing in Earth sciences is absolutely massive. With classical high-performance computing, we're stuck waiting hours just to render a 7-day weather forecast, and it's locked at a pretty blurry 10 to 50-kilometer resolution. But when you throw quantum computing into the mix, we get that fully optimized forecast in mere minutes and at a hyperlocal resolution of 1 kilometer or less. This visceral difference in processing speed means we can predict an extreme weather event, like a flash flood, with nearly 90% accuracy instead of the usual 80%. That's a real game changer. So, how does that actually play out in practice? Well, it breaks down into 4 steps. We start with step 1, which is satellite data collection at that hyperlocal 1-kilometer level. Then, after we handle transmission and pre-processing in step 2, we hit the real magic. Step 3, quantum encoding and processing. By using advanced algorithms like quantum support vector machines, all that massive climate data gets processed in high-dimensional spaces all at once. This leads directly to step 4, highly optimized forecasts and ultra-rapid anomaly detection. Meaning, we can spot an impending heat wave or a severe flood long before a traditional computer would have even finished rendering the initial data.
Section 3. Accelerating Aerospace Product Design, shrinking decades of development into years.
You know, aircraft and spacecraft are dealing with enormous safety parameters and ballooning development budgets, but quantum computers are poised to compress this massive design-to-manufacturing cycle. They do this by accelerating computational fluid dynamics and enhancing finite element analysis, which allows engineers to simulate high-fidelity aerodynamic designs far earlier in the process. And because quantum mechanics actually mirrors subatomic matter, these systems can accurately predict how brand new advanced materials will perform at a molecular level under extreme natural conditions, all while utilizing incredibly fast machine learning for flawless manufacturing quality control. Section 4. Optimizing complex financial markets, solving exponential combinatorial problems. Switching gears entirely, the finance industry is, quite frankly, choking on complex data structures and endless regulatory hurdles right now. In trading today, we aren't just dealing with a simple equation anymore. Under what's called the XVA derivatives umbrella, we have credit,
debit, funding, capital, and margin valuation adjustments all interacting with each other simultaneously. The complexity of these trading models is skyrocketing exponentially. Money managers desperately need the quadratic speedup that quantum computing provides just to be able to simulate these massive, tangled scenarios, estimate their expected returns, and rapidly rebalance their portfolios against intense market volatility.
But what's truly fascinating is that this isn't just a tool for Wall Street hedge funds. 1.7 billion, that is the number of completely unbanked adults globally today. Quantum's superior predictive modeling can sift through immense mountains of behavioral data in an instant to seamlessly tailor specific credit products directly to them. This technology literally has the sheer processing power to expand global financial inclusion on a scale we have never seen before.
Section 5. Sensing Earth from Space. Atoms as the ultimate gravity sensors. Okay, this is straight from NASA. We're talking about a magneto-optical trap gravity gradiometer. In simple terms, instead of using clunky mechanical parts to measure gravity, this device uses laser-cooled cesium atoms as the test masses themselves. By launching these incredibly, unbelievably cold atoms in a fountain and leveraging quantum particle wave duality, the atoms effectively act as matter waves. The system then measures the minute phase shifts that happen when Earth's gravity distorts those matter waves, giving us unbelievable precision.
And the wildest part? This dual-trap system achieves an astonishing 140 decibels of common mode noise rejection. Practically speaking, that means it completely filters out the chaotic background vibrations of the environment or the spacecraft itself. It leaves scientists with only the pure, highly accurate gravitational field data.
Taking this exact sensor up to space is a total revolution. See, down here on Earth, gravity pulls those atoms down instantly, giving you just a tiny fraction of a second to actually measure them. But put it in the microgravity of a satellite orbiting Earth, and the atoms are totally drag-free. You get a massive 10-second interrogation time. That unlocks a mind-bending sensitivity of 10 to the negative 13 Gs. That extreme level of sensitivity allows us to map hidden underground aquifers, track tiny shifts in ice sheets, and even monitor ocean bottom pressures entirely from orbit.
Section 6. The coming societal transformation, security, economics, and the new global paradigm.
This kind of immense computing power obviously brings a really profound dual nature to society, ushering in what experts call a new quantum security paradigm. On one side of the coin, quantum computing threatens to eventually break the classical encryption methods we use for basically everything today, which understandably raises massive concerns about enhanced data mining and mass surveillance. Yet, on the flip side, it simultaneously offers the ultimate solution, the development of quantum-resistant cryptography. We are looking at a forced global transition in how we protect data across absolutely every network. Society is going to have to carefully navigate both the security risks and these unprecedented protective innovations.
Which brings us to a pretty stark reality about the current landscape. As IBM Research bluntly put it, when demand exceeds supply, organizations that have not already established access to quantum computers may face long waits. The line is forming right now, folks. Organizations absolutely must start building quantum-ready talent, experimenting with these new algorithms, and exploring hybrid classical quantum systems today. If a company waits on the sidelines until the technology is completely perfected, they risk a severe competitive disadvantage that they simply might not ever recover from. So, the absolutely crucial question we have to leave you with today is this: is your industry ready for the quantum era? As we've unpacked in this explainer, the quantum leap isn't just some future possibility reserved for theoretical physics labs. It is happening right now across climate science, aerospace, high finance, and global security. Think about how fast your own sector is going to be forced to adapt, and what exactly happens if you're the one left behind. Thanks for joining me on this explainer, and keep exploring,